Hello APC Mechanics students in Unit 7 Gravitation, Class 2, 7.1 Gravitational Forces, Part 2. Section 1 Orbital Period of Planetary Motion. Okay. Another important feature provided by Newton's universal law for gravitation is the period of planetary motion. Consider a planet of mass capital M and a moon of mass small m separated by distance r from center to center. Then there will exist a gravitational force that couples both massive bodies, and assuming the moon is much less inertial than the planet, so that's the pull of gravity, and because the moon is much less inertial, we will consider that the moon is only rotating around Earth. The aim of this section is to determine the orbital period of the moon around Earth. In the previous class we have determined the orbital speed, and if you recall, it was given by v to be the square root of gm divided by r, in which m is the central mass. And we have stressed on the fact that this relation can be only used whenever the moon or the satellite is performing perfect circular orbits. Assuming that the moon is given an initial velocity tangential to its orbit, and this is important because whenever the velocity is completely tangential to the acceleration, then we're in case of circular motion. The forces acting on the moon are the pull of gravity, represented here in the FBD, and now we can apply Newton's second law given by F net is ma, which is basically Fg is ma. Fg is the only force that is acting on the moon. Now we can project along the radial or the centripetal direction. That would be Fg is mac. Now Fg is completely lying along the radial or the centripetal direction. For this reason we don't have cosine or sine, and the acceleration will be changed to centripetal acceleration, which then will be related to speed by v square over r. Now we can apply the cancellation effect for the masses and the radius or the distance. And remember that the title of this section is the orbital period. We're interested in determining the period, which is capital T. And what does the period represent? It's the time taken for the moon to complete one complete revolution around the Earth. And in this case, so gm over r is equal to v square. Because we're assuming that the speed is constant due to the perfect circular orbits, then we can say it's distance over time. And the period is the time taken to complete one revolution, and corresponds for one complete circular revolution, which is 2 pi r, which is the circumference of the orbit. Now replacing them here and replacing again the speed in the above expression, we would get that would be gm over r, which is equal to 2 pi r divided by t to the power of 2, and we're interested in determining capital T. Performing the square root and isolating t square, that would be square root of 4 pi square r cube divided by gm. Then the orbital period of a moon or a satellite orbiting a central mass would be given by that. Now what are some important features? The orbital period formula works for any object rotating around another massive object. In particular, it works for moons and satellites. The orbital period of the rotating body depends only on the central mass and the separation distance. It doesn't depend on the mass of the body which is rotating. Here we're assuming that the orbit is perfectly circular and the speed remains constant because r is constant. In reality, the orbits are elliptical, and we will see how the change in the radius can be taken into consideration using the conservation of angular momentum. Now, section 2, gravitational force, and a very important skill, which is the linearization. Now, as we have said several times, this is the pull of gravity exerted between two massive bodies separated by a very large distance. Now, assume the central mass has a radius r, then the gravitational force is strongest at the radius of the planet, that is when r is equal to capital R. Okay, so we are talking about the force exerted by the central mass on the moon. So because the pull of gravity is inversely proportional to the distance, so as the distance increases, the pull of gravity decreases. And we can see the following: when is the pull of gravity greatest? When this moon is closest to the central mass, and we're assuming at the surface, that is when small r is equal to capital R. And if you're interested in the plot of the curve, we're plotting the pull of gravity as function of r. So notice that as the distance r increases, the pull of gravity becomes weaker and weaker, it decreases, and it has the greatest value at r equals to capital R. And for r less than small r in this region, notice that we didn't plot any curve, because this formula only applies whenever we are away from we're not inside the mass, we're outside the mass. Now, one feature often implemented is linearization, which is changing the curve from being hyperbolic or any type of curve into a linear curve. This is done by plotting fg versus 1 over r square in this case. Then let's consider another curve, which is given by the pull of gravity versus 1 over r square. Now, why this curve is important for us? Let's see. Because the pull of gravity can be written in the following form. If we drag gmm out, that would be gmm multiplied by 1 over r square. And if you compare it with the equation of a straight line, which is given by y is equal to ax plus b, we can notice that y represents the pull of gravity, and the variable x represents the variable which is 1 over r square, and the y-intercept would be in this case 0, because here we don't have anything, which means it's plus 0, and the slope would be identified by this term, which is gmm. And by changing the labels of the curve from being fg versus r into fg versus 1 over r square, this means the type of the curve changes from being hyperbolic to straight line, where the slope is given by gmm, which allows us to measure the mass of either knowing the other. The slope can be determined using the best fit line of such curves. And suppose that if we know small m, we can determine capital M. Now, section 3, gravitational force inside a planet. The gravitational force between two massive bodies m and m is given by that. Now here, we can apply this formula whenever the small mass is outside the planet. Assume the central mass has the radius capital R. Suppose we are interested in determining the gravitational force exerted on the mass m, but now the mass m is located inside the planet such that r is less than capital R. Suppose now we are interested in determining the pull of gravity on small m, in which m is located inside the central mass. The gravitational force should be changed into Fg, which is gmm prime over r square. If you compare both formulas, the difference is that the central mass has been changed to m prime. What does m prime represent? Where m prime is the mass located inside the central region and not the total mass, and we have m prime is less than m. Because we are interested in determining the pull of gravity on this small mass m, then we can use this formula, but in this case we cannot use the capital M, because the capital M represents the total mass enclosed inside the capital radius. However, now we're interested in determining the pull of gravity due to the mass exerted by the mass enclosed by small r. For this reason, M prime would represent the mass contained in this small radius. Okay. If the central mass capital M is of uniform mass distribution dictated by rho, remember that rho is the density, then we can say that the density is capital M over V, which is the capital mass divided by the total volume. Here, if you look carefully, we are saying that the mass is uniformly distributed along the volume and it can be related to the density, then the density is mass over volume. So generally speaking, we're saying that rho equals to mass over volume. These two quantities, mass and volume, they should be related to each other. So if we're talking about a specific mass, we should talk about the specific volume that is related to this mass. What do I mean by that? Here, because we have said it's mass over volume, this mass represents the total mass of the planet. For this reason, this volume would be the total volume of the planet dictated by the larger radius capital R. We can say, because the mass distribution is the same, It is also equal to m prime, but what does this mass represent? This is the mass enclosed in the small radius. For this reason, this volume should be the volume of the smaller radius and not the complete volume. Okay, so this equality is important. And here in this case, we're interested in searching for m prime, because m prime is needed to be replaced here. Now 4/3 pi they cancel, and okay, we can isolate for m prime. Now m prime can be written as r cube over capital R cube multiplied by m, and this can be replaced in the initial relation that we have. Then the pull of gravity can be written as follows. Here we apply the cancellation effect. R cube cancels with r square with the left node r. Then it can be written as gmm over r cube multiplied by r. Then the gravitational force exerted on a body of mass m inside the central mass is given by gmm over r cube multiplied by r, where r is less than r. And the dependence of Fg on r in this case is linear. Notice carefully here, initially when we started with the pull of gravity outside the planet, it was proportional to 1 over r squared. Now inside the planet it's proportional to r. Then outside the planet is hyperbolic, and inside the planet is linear. This is a very important result. So for r is greater than r, the gravitational force is given by gmm over r square, dictated by the inverse square law, and the shape of the curve is hyperbolic like that. And now because we skip the part in which r is less than r, but now we know that it's linear, and we know that it should be continuous at this point, so we can connect the origin to this point via a straight line. Okay, so that's the completion of the curve from 0 to r. Now section 4, gravitational force inside a whole planet. Now you can consider this section just as a remark. Consider a whole planet of mass m and of radius r, where the mass of the planet is contained only on the surface. By a whole planet we mean that the mass is only contained on the surface. Inside the planet we don't have any mass. We are interested in determining the gravitational force exerted by m on another mass m that is at a radial distance r from the central mass. We will distinguish between two regions, region 1 outside the planet and region 2 inside the planet. Outside the planet, without surprises, the gravitational force would be given by gmm over r square. Now region 2 inside the planet, because we're talking about inside the planet at a separation distance r from the center, inside this region we don't have any mass because the mass is contained on the peripheral or on the surface. For this reason there is no pull of gravity. And now let's solve the following problem. A spherical non-rotating planet has a radius capital R and uniform density ρ throughout its volume. Suppose a narrow tunnel were drilled through the planet along one of its diameters, as shown in the figure above, in which a small ball of mass m could move freely under the influence of gravity. Let r be the distance of the ball from the center of the planet. Here we have a planet. They didn't give us the mass of the planet, however they gave us the volume indirectly by giving us the radius, and we have the mass distribution, which is ρ. And through the planet there is a narrow tunnel which is drilled of very small dimensions, and we have a small ball of mass m that can move freely along this tunnel. The distance from the center to the small mass m is denoted by small r. In part A, we need to show that the magnitude of the force on the ball at a distance r less than r from the center of the planet is given by F is minus cr, where c is a constant given by 4/3 pi g rho m. Now we know that the only way to determine this force is using Newton's universal law of gravitation, which is given by Fg equals to gm m over r square. But now because we're talking about the pull of gravity inside the planet, this should be m prime, and m prime is the mass contained inside the orbit or the radius r. For this reason, let me say that let m prime be the mass contained inside of r, And before I continue, notice that here the force have been, or they have represented, or they have introduced the force in the following form with a negative sign, and we've said that the pull of gravity is given by m over r square. Now this is the magnitude. This is the magnitude. Okay, this is the force itself. This is the force. And here they said that show that the magnitude of the force. This is wrong. This should be show that the force. Show that the force. Okay. So they want the force and not the magnitude. Why it's minus? Because it's always pointing toward the center. If we're talking about radial direction, this is a radial direction. Any force pointing away from the radial direction like this is considered to be the positive direction. Any force considered to be pointing toward the radial direction like this is considered to be a negative force. So I'm trying to explain why they have introduced this minus sign. Okay, in order to do so, we need to determine the mass m prime contained inside of R, then proceed with the Newton's universal law of gravitation. So this is done using density. Density is given by ratio of mass over volume. If this is capital mass, then we need to use the total volume, which is given by 4 over 3 pi r cube, in which r is the total, the larger radius. And that would be equal to m prime over 4 over 3 pi r cube. So this is the mass contained inside of small r. For this reason, I'm using the smaller volume. And we're interested in determining m prime. Now, why I'm not using this fraction? Because simply we don't have capital M, we have rho. Then m prime can be isolated, and it's given by rho over 4 over 3 pi r cube. Now we can use Newton's universal law of gravitation, and notice that I have used the form which is the force and not the magnitude in order to compare it with this perfectly. Now replacing m prime, which is given by rho 4 over 3 pi r cube, applying the cancellation effect for r, it will become linear. Comparing it with minus CR, we notice that we have achieved the following form, and indeed C would be given by 4 over 3 pi g rho m. Then we can say that the force of gravity exerted on the small mass m inside the narrow tunnel is given by minus CR, with C given by 4 over 3 pi g rho m, g being the gravitational constant. On the axis below, sketch the force on the ball as a function of distance r from the center of the planet. We know that outside the planet, the curve would be hyperbolic. Inside the planet, it would be linear. So we expect that inside the planet, it would be something like that. And outside the planet, it will decay away from the planet. But notice that we're interested in sketching the force and not the magnitude. So it would be negative, and it have the following form. So this is linear inside the planet, and that's hyperbolic outside the planet. Now the ball is dropped into the tunnel from rest at the point P at the planet's surface. So we're gonna release mass m from this point, and there will be a pull of gravity acting toward the center of the planet, so it will move to the right. Due to the exerted force, it will reach this point with a gain in speed. Now in part C, determine the work done by gravity as the ball moves from the surface to the center of the planet. So let's recall some notions related to the work done by a force in general. If the force and displacement are parallel, the work is given by Fd. If they are anti-parallel, it's given by minus Fd. If they are perpendicular, it's given by 0. If they are angled, it's given by plus minus Fd cosine theta. All of these apply if the force is constant. However, if the force is not constant, we need to promote the work done to be given as a line integral of f dot dx from initial position to final position. And remember that the order of the boundaries are very important. Usually some integrals can be calculated like an area integral or a volume by placing the lower bound to be the smaller value, and the upper bound to be the higher value. Whenever we're talking about line integrals, and especially the work done by force, we need to take into consideration that the lower bound is the initial position and the upper bound is the final position, independent if one is greater or less than the other. So for this reason, I will say that the work is given by F dot dx. Now why I have used here dot dr? Because the variable that we're talking about of position is r and not x. Our initial position is the point P, which is at a distance capital R from the center, and the final position would be the origin itself. Now what does this mean? F dot dr, it's the projection of the force along the radial direction. Now, independent whether we're moving to the left or to the right, dr is always assumed in the positive direction to be radially outward, and the force is pointing toward the center. So in this case, F dot dr would be minus F dr because they are anti-parallel, and in this case F represents the magnitude, and the magnitude F is given by C multiplied by R. So this would be given by minus CR dr. Okay. Now taking the minus sign, or let's substitute F by CR. Now C is a constant, R would be R square over 2, replacing, so this should be computed once at 0 and once at R, and the answer will be given by CR square over 2. Then the work done by the gravity as the ball moves from the surface to the center is given by CR square over 2. And now in part D, we need to determine the speed of the ball when it reaches the center of the planet. And in order to determine the speed, you need to think about the previous part. In the previous part, we know that work has been exerted by force, and the result is given here. And whenever a work has been exerted by force, which means that speed has been injected, and the speed can be determined by the work energy theorem, which states the variation in kinetic energy is equal to the work done by the external forces. The only external force acting on the mass m is the pull of gravity, and the work is given by the following expression. Now, because the mass m has been released from rest, which means the initial speed is 0, then the kinetic energy initial is 0. Kinetic energy final is half mv square. V represents the speed of the ball at the center of the planet. Now cancellation effect for half, then v square is given by cr square over m, then the speed is given by the radical of cr square over m. Then the speed of the ball as it reaches the center is the following. Now in part E, we need to fully describe the subsequent motion of the ball from the time it reaches the center of the planet. So since the force of gravity inside the planet has a restoring form, F is given by minus CR, so this should remind you by the force which is similar to Hooke's law, minus kx, and since we're talking about proportionality or linear, the force is proportional to position. Now, going from P to the center, there is a force, a restoring force, that is pushing M to the center. Now M at this point will gain some speed, and it will continue moving toward the left because it's inertial. However, the force in this case, it won't be pointing to the left anymore, it would be pointing to the right, which will be again exerting, or so it will be pulling M toward the center again, which is very similar to what happens in a spring. Then the type of motion is simple harmonic motion, because the force is proportional to position, it has the restoring form. Eventually the ball will reach the center and continue to the end of the diameter and continue oscillating in this manner, which is perfectly as the horizontal spring. Now in part F, write an equation that could be used to calculate the time it takes the ball to move from point P to the center of the planet. It is necessary to solve, it is not necessary to solve this equation. Now going from P to the center of the planet, this represents half a period, a quarter a period, because a period would be going from one end of the diameter to the other end and returning back. So this would be period over 4. They're telling us it's not necessary to solve this equation that allows us to calculate the period, but write an equation that can be used, and this is done using the differential equation. So let me say apply Newton's second law, which is F net is ma. The only force is minus CR is equal to MA. A can be changed to the variable R using calculus. So this is the differential equation then that can be used because it obeys the form which is r double dot plus omega square r is equal to 0. And this can be used to find the period because omega square can be determined in terms of C over M. And this is what we have done for a horizontal oscillator. And now for the rest of the video we're gonna solve some exercises. Exercise 1, a student is asked to determine the mass of Jupiter, knowing which of the following about Jupiter and one of its moons. So Jupiter is the central mass. Will allow the determination to be made. The time it takes for Jupiter to orbit the Sun, this is not important. The time it takes for the moon to orbit Jupiter, yes, this is important. This is the orbital period. The average distance between the moon and the Jupiter, this is important, which is r, because remember that the period is only related to the central mass and the orbital period, making 2 and 3, which is E, to be the correct answer. Now consider Earth to be stationary and the moon is orbiting Earth in a circle of radius r. If the masses of Earth and the moon are me and mm respectively, which of the following represents the total mechanical energy of the Earth-Moon system? This is important and will be visited again. The total mechanical energy is given by K plus UG. Now suppose that, so the kinetic energy is the energy of the Earth and the moon, so that would be half me VE square plus half VM square. Now what about the gravitational force? Although here we have two kinetic energies, but the gravitational force would be one, which is coupling me and and that would be given by minus G me over r. So remember that for planetary motion, the gravitational potential energy is given by UG minus G over r. So even if we have two masses, m and m, the gravitational potential energy would be one term coupling m and capital M. Now here, because the moon is less inertial than the Earth, we're assuming that the Earth is very inertial and its kinetic energy is almost zero because it's not moving. So that would be half VM square minus G me over r. But if you notice at the choices, we need to work out this expression in order to put it in the following forms. Vm represents the speed of the moon, and we know that if we're talking about circular orbit, Vm can be written as the square root of Gm of Earth divided by r, where m of Earth is the central mass, so this can be written as half me. Now the power 2 cancels the square root, that would be g, or let me state it here, Gme over r to the power of 2. This cancels with that. Okay, so sorry, I have done a mistake here. This should be mass of the moon. Minus G me over r. So let me use capital R everywhere. So that would be half G me over capital R minus G me over capital R. Now we can factor out these two and we're left with half minus 1, which is minus half. So that would be minus half G me over capital R, making C to be the correct answer. Spheres X, Y, and Z have the same masses and locations indicated in the figure above. What is the magnitude of the net gravitational force on sphere X due to the two other spheres? So we're interested in the gravitational force on the sphere X. Now only sphere X and Y have the same masses, but the sphere Z has 2m. So we're interested in the pull of gravity on m. Now here we have two forces. We have the force exerted by z on x and by y on x. Even y exists midway between x and z, z will also exert the force on x. So we have both of them will be pointing toward the right. So let me now start by y on x, which is g m on over r square plus g m multiplied by 2m over the total distance from here to there, which is r plus 2r, which is 3r. Now we can factor out gmm over r square. That would be 1 plus 4 over 9, and that would be 9 over 9, which is basically 13 over 9 gmm over r square, making, sorry, it would be, this is 2, which is 11 over 9. Identical satellites x and y of mass m are in circular orbits around a planet of mass m. The radius of the planet is capital R. Satellite x has an orbital radius of 3r and satellite y has an orbital radius of 4r. The kinetic energy of x is kx. In terms of kx, the gravitational potential energy of the planet x system is... So we're interested in determining the gravitational potential energy between the planet and the satellite x in relation with x, kx. So the gravitational potential energy is given by minus g, the mass. Here we need to identify the masses of our system. We have the planet and the satellite x. The mass of the planet is given by capital M. The mass of the satellite is given by capital. So identical satellites of small mass m divided by the radius or the separation distance, which is 3r. So basically this is UG of the system. Now in order to find the relation between UG and kx, we need to determine the ratio. This is the best way to do it, which is basically UG over kx. Now why I'm calculating the ratio of UG over kx and not kx over UG? Because our answer should be in terms of kx. For this reason, kx, it's better to be in the denominator. Now UG is given by minus g m over 3r. The kinetic energy of the satellite is given by half. The mass of the satellite is m, and that would be v of the satellite. V of the satellite is given by radical g and the central mass, which is capital M, divided by the separation distance, which is 3r. Now notice that this we cannot use unless this we cannot use it before we prove it, but here because it's an MCQ we're allowed to do so. Now that would be minus g m over 3r divided by half m radical of g m over 3r to the power of 2. Now power of 2 cancels with the square root. G with g cancel, the masses cancel with the masses, r cancels with r. We're left with minus 1 over 3 over 1 over 2 times 1 over 3, which is basically minus 2. Then UG over kx is equal to minus 2. Then UG is equal to minus 2 kx, and the correct answer in this case is A. Now final exercise 5 as an exit ticket. A scientist measures the magnitude of the gravitational force G of an asteroid at different locations near its surface. The data are represented in the graph of G as function of the distance r from the asteroid center as shown. Which of the following is a modification the scientist could make to the graph in order to determine the mass capital M of the asteroid, and explains how the mass can be determined. So if you notice carefully, they're talking about a skill which is linearization. G is given by gm over r square. The linearization happens here if you factor out 1 over r square, that would be gm 1 over r square. Then basically to determine the mass, you need to linearize the following. Plot the g as function over 1 over r square, and the slope would be gm. So we can directly eliminate these. Then graph 1 over r square, and the mass of the asteroid is equal, so the slope is equal to gm. Then the mass would be the slope divided by g. So it's the slope divided by g, making d to be the correct answer. Then that's it for me in this video, guys, and see you soon in a new one.